Okay. Let's get started. So, good morning, everyone. Welcome to digital logic design, digital logic design course. So, can you hear me? Well, it's okay. Okay. So, this is the English teaching course, right? So, I will, I, I will teach in English, right? So, as you expected. So. So today is the first class of this course. So I will briefly introduce about the this digital logic design course. So okay, so as you can see, I'm using Zoom, and then I'm sharing my screen with the Zoom. So actually, so I believe Zoom has some delays. So it's because my screen is connected via some internet. So, but I believe it's okay. So and then so you know so actually so we start a Zoom lecture because of COVID, but so actually the benefit of Zoom is that so we can record this lecture. So and then usually I share the recorded lecture on YouTube, so you can watch the recorded lecture on YouTube after the class. So okay, let's start. So this is the digital logic design course for computer engineering students. Okay, and then what's the object of this course? So this is the hardware related course. Okay. So this is the hardware related course. So we will learn about the hardware. Okay. So as you can see, this is the digital system, right? So that means that we will learn how to design digital systems. And then so actually for this course, so this course is the very fundamental course. So which means that this is the basic course. Okay. So in this course, we will learn how to design basic digital logic gate. Okay, so we will learn about the basic digital logic gate. Okay, so you can find this terminology has 4 words. Okay, what's that? What are those? Okay, basic. So it's a very basic, simple, and digital. So digital means that the signals or information has only 2 kinds of signal or data, 0 and 1. Okay, and then what is the logic? So actually, in a real world, we use logical. So what does that mean? So logical means that it's reasonable, right? But so in this course, the logic means that if some kinds of input is provided, then output is simply determined by input signals. So it is called logic, right? And then gate. So gate is the very simple component that is used for building very complex digital systems. So we will learn about the very simple digital component or simple digital logic in this course, right? So, and then we will also explore how to design digital blocks. Okay, so those are object of this course. So what will be covered in this course, as you can see? So we will learn basic concept of digital logic design, and then also you can find the basic logic gates here, the second line, NOT gate, AND gate, OR gate. So we will learn how digital logic, the output of digital logic is determined by very simple logic gates. So that is kind of promises, okay? Like the 1 + 1 = 2. It's a very simple arithmetic logic. So, but we will learn about the logic gate, so digital logic gate. Okay, and then so we also learn about the very simple, so basic knowledge on CMOS transistor. So you can find the transistors here. So what are transistors? Okay, so I believe the most of you are computer science or computer engineering students. So transistors are some basic component that is used for building semiconductor logic, semiconductor circuit. Okay, so actually, so you know, the Intel CPU or NVIDIA GPU, so those processors are called chips, right? So like those processors are called processor chips, but we already know that those chips are based on the semiconductor technology, 반도체 in Korean, semiconductor technology. And then what does that mean? Actually, using the semiconductor technology, we can build transistors. Okay, and then using transistors, we can build basic logic gates. So actually, so I believe you are very familiar with some software or applications, but those software or applications are kind of, it's a kind of some code, okay? Code, and it's designed based using codes, like some languages, programming languages, but in order to run software, we require hardware, right? So actually, software runs on hardware. So hardware is the real world, okay? So I frequently say that software is the kind of it's kind of a fantasy world, but the hardware is the real world. So in order to run the software, and then actually the software data is translated into the digital signals. It's a kind of electric signals, and by using or by processing these electric signals, we can generate outputs. Outputs defined by software. Okay, so hardware receives digital signals generated by software, and hardware generate output or output signals or output data defined by software or systems. Okay, so we need to understand how hardware works in the computer systems. But in order to, you know, the hardware systems are very, very complex. So you know, the modern computer systems are actually very complex. And then, so it's very hard, it's very difficult to build these complex systems, right? So we can start from the very simple component, such as the basic logic gate. And then in order to build the basic logic gate, we need to use the transistors. Okay, this is the kind of fundamental component for building semiconductor devices. Okay, so we will learn the basic knowledge on CMOS transistors. So you know, recently the semiconductor industry is very critical. So for you know, the United States is prohibit some so exporting of the GPU chips to China. So this is something that, and they protect their semiconductor manufacturing technologies. Okay, so it's the same for the same to the Korea government. Okay, you know, the semiconductor technology is very critical. So it's a top secret. Okay, so they protect the some semiconductor technology or semiconductor industry in the nation. So very important. Okay, Then in this course, so we will learn about the Boolean algebra. So I believe you are familiar with the terminology algebra. What is it? What is algebra? In Korean, it's called 대수, right? What is algebra? So you can understand that. So algebra is a kind of equation, right? So like A plus B equal C, right? So, but in this course, we will learn about the Boolean algebra. So actually, the Boole is the name of a person, a scientist. What is Boolean algebra? So we will learn. Okay. So actually, we use Boolean algebra to build digital circuits or digital logic. Okay. So based on this basic logic gates, we can build more complex logic. So and then but based on this Boolean algebra. Okay, so it's kind of algebra like A plus B equals C. Okay, but it's related to the digital signals. Okay, and then we'll also learn about the Kahneman. So it's used for optimizing Boolean algebra. And then we will learn about the combinational and sequential logic design and FSM, and then memory arrays. Okay. So and then so these are some basic knowledge we will learn in this course, right? And then I believe so you are taking this course because of computer architecture course, right? So you know the computer architecture is the mandatory course in computer engineering department or computer science department. But you need to understand the basic logic or basic design process or basic hardware component in order to understand the hardware architecture of computer systems. Okay, that's why we learn. So that's why you are taking this course, I believe. Okay. Also, in this course, we will learn about the hardware description languages. Okay. So what are languages? So we use programming languages for building software, right? So in order to make a certain applications, we can use programming languages such as Python or C or C++, Java, something like that. Then, actually, in this course, we will learn about some new languages. It's called those languages are called hardware description languages. It's called the HDL. Then actually we will use the system Verilog. Okay, so this is also a programming languages. Okay, like C, it's very similar. The structure of system Verilog is very similar to C, not Python. So you know the Python and C are different kind of programming languages, right? C is the compiler-based language, and Python is the interpreter language. So actually, the Python is very slow because the Python is the interpreter language. But the system Verilog, the structure of system Verilog is very similar to the C. Also, this code, the code written in system Verilog can be compiled, okay, like C, compiled into the basic logic gate, okay. So actually, in order to design digital systems, we use hardware description languages, right? So it's similar that. So actually, in order to make an application, it's a binary code, right? So you know, actually, the binary code is composed of digital signals 0 and 1, right? So we cannot use these zeros and ones, the digital data for building binary file, right? We can write a very simple and then very convenient code written in programming languages, and then this code is translated into the binary code, binary data. So likewise, it's very complex. So it's very difficult to build this system directly from transistor. Okay, it's very complex. So we use programming languages. Okay, and then this kind of programming languages are called hardware description languages. Okay, so like C, we can write the code, and then this code is compiled, and then based on the compiled code, we can build hardware. Okay, so those are what we will learn in this course. Okay. Okay, textbook. So in this course, I will use this textbook, digital design and computer architecture. Okay, so this textbook includes some part of digital design. And then also this textbook includes the computer architecture. Okay, so I believe you will learn about you will take the computer architecture next semester, right? So I recommend you to purchase this book. I believe this book is very great book. Okay, it's very great. So I recommend. Okay, so and then in this course I will use some lecture slides like this. So I will post the lecture slides before the classes, and then also, as I mentioned, we will use the system dialog for some design maps. So we will use the EDA tools. So EDA means that electric design. What is A? It's automation. Electric design automation. So like some programming languages or ID tools for the programming languages, we will use the EDA tools. Unfortunately, I found that this book is very expensive in Korea. So you can purchase the ebook. Okay, so from this site. So I'm not related to this company, but I found some cheap option for this book. Okay. So, and then also I recommend. So I know. So you are very familiar with some lectures, the video lectures. Also you are very familiar with this lecture slide. So the teaching using lecture slide, but I believe the reading is also very important. Okay, so I don't believe you can get enough information or enough knowledge from the lectures. Okay, so you need to read the textbook. Okay, this is very important. Okay, so this is the English book. So understanding some English languages is also very critical in this field, right? Okay, so I hope you can practice. You can practice reading some English books, English textbook for this course. Okay, prerequisite. So we will use, so as I mentioned, we will use EDA tools. So electric design automation tools. So these tools are electric design automation tools. So actually, and then also we will use system development, right? And then I mentioned that if you write some codes using system Verilog, you need to compile. What is required? So I said we need to compile the written code. So what is required? Compiler. Okay. So like C, so you have to make the binary file from C code. So we require compiler, right? Also, you have to use Python. We need to use Python interpreter. It's called the interpreter, not compiler. Okay, because Python is the interpreter-based language. So actually, it means that we need to install compiler. Well, you need to install EDA tools on your computers, right? But in order to install these tools, we require Linux, not Windows, the Linux operating system or Mac operating system. So if you are using a Mac, I believe you are familiar with the CLI. It's a command line interface, like it's different from the GUI of Windows. Okay, so but most of tools run on command line interface for this course. Okay, so for this course, you need to know some basic knowledge on Linux operating system or Mac operating system, right? And the CLI, not GUI. Okay, so it means that you need to use some very basic commands on Linux operating system or Mac CLI. Okay, like a CD, CP, RM, something like that. So very basic commands. This is because so we will use COSE Verilog. So this is the compiler, so kind of compiler for system Verilog, and then this tool runs on Linux operating system or Mac, not Windows. Okay, but fortunately for Windows users, so you can use WSL, so Windows Subsystem for Linux. Okay, so it means that you can also install Linux virtual machine. So Linux CLI virtual machine on your Windows operating system. So you can click this link for some detailed information. So, but you know, so this is this logic design course. So I will not teach about the Linux operating system, right? So, but you need so for the design maps, so you need to install. If you are using Windows operating system, then you need to install the WSL or VirtualBox. You need to install Ubuntu, like some kind of Linux distributions using VirtualBox. So if you are interested, you can click. So as I mentioned, I posted these lecture slides on the Blackboard, right? So you can click this link, and then you can get familiar with some Linux operating system on Windows. Okay. Instructor. So my name is Kwanje Ku, is Kwanje, and then also this is my office, and then the office hours are Tuesday or Thursday 1 p.m. But please email me before the appointment. Okay, and this is my email, and then this is my lab page. And then, my research area is computer architecture. So I believe I can teach computer architecture next semester. Okay. And then for this course, there are two teaching assistants. And then, so you can find the email address information of teaching assistants. Okay. So he's a freshman, so fresh master student. So email is not yet provided. But this is very important. Do not email TAs regarding homework and lab questions. Post your questions on Piazza. Okay. So, so actually, in the previous courses, the TAs received many emails from students, but the questions are very repeated. So which means that the questions are very similar. But if individual students send email to the TAs, then TA will get many similar emails from students. It's very inefficient. They are also students, so they also need to study. Also, they need to do research during their coursework. So their time is also very important, right? So do not email TAs regarding homework and lab questions. Also for the attendance, so they cannot process the attendance issues. So for the attendance issues, so email me, okay? Not email TAs. So post your questions on Piazza. This is very important, right? So what is Piazza? So Piazza is the class management tool. So you know, at Korea University, we use a Blackboard as a class management tool, but interface is not good. So I use Piazza. So on the Piazza, you can post any questions, and any student can post answers also. Okay, like this. Also, TAs or I will also post answers regarding questions. Okay, so please use Piazza, not email. So for the email, so if you have some issues regarding attendance or some classes or some if you can make an appointment, email me. Okay, but regarding the homework questions or lab questions or something like so you need to post your questions on Piazza. Okay, so this is the course web page. So actually for the Blackboard, I will use Blackboard for posting announcement and assignment. Okay, so Blackboard provides the links to Piazza. Okay, and then this is the Piazza link, and then you need to join Piazza as a student, not an instructor. Instructor is me. Okay, as a student, and then you require access code. So access code is the Hermione. 뭐 헤르미온이라고 불리긴 하지만 정확한 발음은 허마이니입니다. Hermione. So I believe some. If you are interested in Harry Potter, then you can find that this is a very familiar name of the heroine, right? Hermione. So I will post some class materials on Piazza, the slides like videos, the recorded videos or some materials on Piazza. Okay, but this is important. Anyone can post questions and answers on Piazza. Okay. Sometimes this is not fixed, but sometimes some students post very good answers. Okay, so in this case, I will endorse these answers posted by students, and then this is not so this is my plan. So if some students can get some endorsed answers, then I will give some some attendance score. Okay. Okay. So you can find. So this is some example from the computer architecture course. Okay. So you can find some lecture slide. So your lecture video here. This is the resource tab of the Piazza. Okay. So this is in-person classes. The Zoom link may be provided if you cannot attend a class. Okay, because of your some illness or some reserve person, you cannot. Okay. So if you cannot attend the in-person classes because of illnesses or some other issues, then you can request the Zoom link. Then to me, then I will provide the Zoom link. Okay. Grading parallels. Okay, this is the tentative grading parallels. So you can find attendance score here. So as I mentioned, if you get some endorsement from me, then you can. I will give some additional attendance point to the students, endorse the students. So then this is the some tentative grading distribution. Like midterm, we will have two exams, midterm or final exam, midterm and final exams, and then assignment. So I will provide some questions related to the what you learned, and then also this course will have some lab assignments. Okay, so we will use you can practice the system value for this using these lab assignments. Okay, exam, on-site exam, closed book, and then you can answer in Korean or English. So this is saying, so for the assignment, even though this is English teaching course, so you can answer. You can also answer in Korean or English for your assignments or exams, right? So you can use Korean. Also, you can ask questions in Korean, right? So English teaching is my duty, not your duty. So you can use any languages, but I can only understand English or Korean. Okay. And this is also important. So this course is so in this course, I will use the self-attendance check. I will not check your attendance manually. I believe this is the kind of waste of time, right? So we will use the self-attendance check system. So in order to check your attendance for classes, then you need to use the self-attendance check link on the Blackboard. Okay, so you can find, I believe you can find the self-attendance check link on the Blackboard. Then you need to check your attendance. And then also for the first 2 weeks, I will not check your attendances. It is because actually the registration can be changed during the first 2 weeks. So I will not check your attendances. Okay, after some registrations are fixed, then I will check your attendances. Okay. So also, this is a very strict rule. So you will get F if you miss more than 1/3, 1/3 of classes, the third of classes, right? So this is the rule is determined by some government. Okay, government. Okay, so this is kind of strict rule. So do not miss checking your attendance. Okay. So tentative schedule for this course, and then please note this day. So please check this day. So this is So we will take a midterm exam and final exam on these dates, April 25th and then June 20th. Okay, during the regular class time. Okay, so please check these dates. Okay, and then class will be cancelled on Memorial Day. Okay? This is because this is the national holiday. Okay? Any questions? No? Okay, so even though this is the first class of this course, so I will briefly introduce about some concepts we will learn in this course. Okay, so this is kind of introductory class, okay, introductory lecture for this course. So digital logic design. So I believe everyone knows that this course is the digital logic design course, but why? Why do we need to learn about the digital logic design? So as I mentioned, so actually I already mentioned during the syllabus some introductory slides, the syllabus slide for this course. But as I mentioned, the digital logic design includes the two important terminology. So it's digital and logic. And what is digital? What does digital mean? As I mentioned, digital is the kind of representation of data or representation of a signal. It's kind of rule. Okay, so it means if we use digital signals, then it means that we will use only two kinds of data, two kinds of digits. It's like the 0 and 1. So we will use only 0 or 1 for representing a kind of signal or data. That means the digital. Okay, so you can understand that this is kind of rule or protocol or promises. Okay, it's just definition. So this means that the signals can be represented using only 0 and 1. Okay, what is the inverse terminology? So it's kind of some opposite rule, like opposite representation of the digital. It's analog. Okay. Okay. So in this course, so we will focus on the digital signals. Then what is logic? So as I mentioned, the logic represents some kind of definition, like 1 + 1 = 2. It's kind of logic. So the definition of logic is a system or set of principles underlying the arrangement of elements in a computer or electricity as a performance specific task. Okay, logic. So why do we learn math? So like 1 + 1 = 2. Why do we learn math? Because we can use mathematics for different tasks. So we can use mathematics for economics, but we can use mathematics for building some models. We can use mathematics for solving some problems. Okay, and then the baseline. The basement of mathematics is the logic. Like so we can define we can learn some definitions such as the 1 + 1 = 2. So this is some kind of logic inside of mathematics. It's the same. In this course, we will learn about the logic of digital systems, or logic of digital signals. Okay, so it's the kind of definition or some principles that is defined in the digital system or digital signals. Okay, so these are very important terminology. So actually, I hope you can understand these principles or terminologies in this course. So why? And then why? So as I mentioned, the computer systems. Computer system is a subset of digital systems. So these are some very popular electric devices we are using in the real world. So, but as you can see that these electric devices are actually computers. Then why? Because these electric devices include processors like a CPU or even the smartphone, or the computers or laptop includes GPUs. So those devices include processors. But in order to build processors, we use digital signals. Okay, so it means that if a system uses digital signals, or system processes digital signals, then those systems are called digital systems, obviously, right? So this is obviously digital systems. It is because these systems use digital signals, and the signals are composed of 0 and 1, right? So actually, the computer systems are subset. Computer system is a subset of digital systems, right? So, and then that means in order to understand. So, as a computer engineering student, you need to understand how a computer system works. If you just learn about some computer languages or programming languages, that means that you can just learn a very small part of computer systems. So actually, as a computer engineering students or computer science student, you need to understand. You need to understand the entire aspects of computer systems, right? It's very important. And then these entire aspects of computer systems also include hardware. Also, some hardware, software interface. Software is a very small part of computer systems, right? So that means you need to understand some very complex and difficult computer systems, which means, but not to understand these complex systems, you need to also understand the very basic fundamental hardware components. So you will learn about the very basic fundamental hardware components in this course. Okay. So why need to learn? Because it's the fundamental core requirement that exposes them to the hardware design. Okay. And then also we can understand how the computer systems are built from these fundamental components. And then it is also very important. If you can understand some computer systems, the aspect of the computer systems, then you can understand how computer programming languages are translated and executed in the computer systems. So you can build more efficient code, more efficient software if you can understand some aspects of computer systems. That's why we need to learn about this the logic design. That's why the computer architecture is the mandatory course in the computer engineering department. I believe some students think that computer architecture is very, very difficult to understand, but you need to learn. Okay. So this is kind of a very funny cartoon. So hardware is here, and the instruction set. This is the hardware software interface. Okay, and then software is here. So when you can find that this guy, so this guy is standing under the instruction frame, and then you can find this guy is very so he looks very difficult, right? Because he is formally standing under this instructions and playing, and then the software is playing something. They are playing above the instructions and playing. So, but this is the fundamental. The hardware is the fundamental system. The computer systems, and and the hardware is also very important. So you know, actually this job coding. Unfortunately, the coding can be also done by AI. Unfortunately, so we can develop AI applications. And humans can develop AI applications by using programming languages. You can write code to develop AI applications. But recently, AI systems can also generate code more quickly and then more precisely. Unfortunately, so this job, unfortunately, this job can be also done by AI. But in order to run AI, they require computer systems, computer hardware. And then in order to run AI applications more efficiently, that means more quickly, then we need to develop more efficient computer hardware, because this is the fundamental system of the computer systems. So I don't know about the future, but maybe the software, this part can be replaced by AI, unfortunately, but we need to develop the hardware system. So that's why you need to learn about the computer hardware or computer systems. Okay? Learning the programming language is not enough. So digital logic is the hardware part in the computer system, and then this is the basic component. The basic component that handles the digital signals, and then using this digital logic that we can build very complex processors. We can build very complex computer systems. Okay. Yes. Also, this course is required for understanding computer architecture. Okay. Okay. Let's learn about some layers on the computer systems. Some people think that this part. Programs are only the part of computer engineering or computer science, but it's not true. So it is because we are working with an entire aspect of computer systems. Okay, actually, the computer engineering department includes this part. This part of computer systems. So we will not learn about the analog circuits or some devices or electric physics under some computer system, but we will learn until this layer. So actually the computer engineering includes these layers, such as the application, so like programming languages, and then operating systems, like a system software, and then architecture, microarchitecture, logic, and digital circuits. Actually, digital, like some usually until this layer. Okay. So actually, the digital circuits can be studied or mainly studied in the electric engineering. Okay. So these are layers. So usually electric engineering students learn until these layers. Okay. So sometimes the electric engineering also includes the system software, like operating systems or embedded system or firmware or embedded software. Okay. So electric engineering can cover until these layers, from the physics to the operating system. Then computer engineering also covers these layers, software, system software, architecture, and then logic, digital logic. So in the computer engineering department, as a computer engineering student, so you will learn about these layers. Okay. Then in this course, we will focus on the logic layers or digital circuit, the part of digital circuits. So as I mentioned, I will briefly explain about some basic knowledge, simple and easy, so basic knowledge on digital circuits, or transistors. Okay. So these are layers you need to learn in the computer engineering department. Okay. Then, what are digital signals? Then think about the real world system. So actually, real world system. So in this real world, we can encounter, so we can experience analog signals, not digital signals. But so what does that mean? So think about the electric wave. So I believe you are not familiar with the electric circuits, but in the high school, I believe if you took the physics, I believe you can understand about some voltage, current in the electric circuits, right? Voltage, resistance, current, right? V equal IR, right? So what does that mean? So actually, so you can use the battery, and the battery can be connected to the lamp, and then connected to some components like the speaker. Then also another node of this lamp can be connected to the another node of the battery. So you can make the electric circuit. But in order to run electric circuits, we require voltage. Okay. So voltage is kind of some potential energy in the electric circuit, and then using this potential energy, the gap of the potential energy, we can run electric devices. So which means actually the signals, the signals or some these are called the signals. Not in the real world electric devices, the signals are analog signals. So which means these are continuous signals. You can define the voltage level here, like here. The voltage level can be changed by time, but these levels are changed continuously. So analog means that this is the continuous. Okay. So signal values are changed continuously. Then we can say that these signals are analog signals, but actually in the real world, all signals are analog signals. Why? The time is continuously flows, right? And then some values like temperature changes continuously, right? Not discretely. You can say that, oh, the temperature changes very discretely, but it's not true. You know, the temperature changes continuously. So like the light, like here, so the intensity of light changes continuously by time, right? So actually, so we frequently use electric devices, and then we can say that, oh, electric devices are digital systems. And then I mentioned that digital systems handle only digital signals composed of 0 and 1. It's discrete. So discrete is the opposite meaning of the continuous. So digital signals just handle discrete signals. But I mentioned that, oh, in the real world, we use analog systems. What does that mean? So we already know that our popular electric devices are digital devices. But in the real world, we use actually analog systems. The real world is working with analog signals. Okay, so as you can see, analog systems handle continuous signals or data, and then the values of analog signals continuously change by time. Okay, time changes, then the signal values can be changed continuously. Okay. Then why these devices are called digital devices? We use these devices in the real world, right? So in order to use the digital devices, the analog signals in the real world is also converted into the digital signals. And why? Why analog signals needs to be converted into digital signals? Why? So as you can see, analog signals are continuous signals. So actually we can find many different values, like 0.0001, 0.0002, 0.00 blah 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 blah. So these numbers are not continuous actually, but we can say that the values are changed very continuously. So what's the problem? Why do you use digital signals? Why? So actually, in the maybe 30 years or 40 years ago, actually the electric devices also handle analog signals, like the continuous voltage levels. But recently, most electric devices are digital devices. Why? What's the problem? What's the problem of our real world? Our real world analog signals. It's difficult. You can say that digital signals are simple. Obviously simple. Why? Because the digital signals have only two kinds of values, 0 and 1. But think about the analog signals, like as I mentioned, the 0.0001, 0.0011, 0.0023, blah, blah, blah. Actually, analog signals can have any possible values. So it's called the real number, right? And then in order to represent these analog signals, we need use very complex number systems, like real number, right? So it's difficult, right? It's not easy. So as you can see, advantage of digital system not require difficult mathematics. So everyone thinks that mathematics are very difficult to learn. Why? It's because the numbers handled by mathematics are very deep. It's a complex system, right? So because it's kind of analog system, right? But this system only handles the 1 and 0, two kinds of data, two kinds of number, right? These systems are much simpler than the analog systems. That's why we use digital logic or digital systems for the electric devices. So another reason of the another advantage of a digital system is that it's reliable against noise. So what does that mean? What is noise? Noise is the undesired. It's not desired. So noise is the kind of additional signal, but these signals are unexpected or undesired signals. So if noises are included in our systems, then our system can work inefficiently or our system can be broken. Okay? Because of noise. Because noise is the unexpected. But analog signal is prone to noise. So it's weak. It's weak against noise. Why? So kind of noise in the real world. So you are listening to some music, your favorite music, but noise is included, then the music information. So the music is distorted, it's a changed, right? Because we are hearing analog signals using our ears. The music is kind of analog signals. But this music, the signals are distorted or changed by noise signals. So analog systems are very prone, so very weak to the noise because the signals can be changed. But digital signals have only two values, 1 and 0. So even though some noises are included in the digital systems, the values are not changed. Okay, that's why. Actually, that's why we use digital signals in our most electric devices. Okay, because so it is because this is very simple, but it's also reliable against noise. This is actually this is the main reason of using digital systems. Okay, it's not difficult. It's not. We don't need to know about some knowledge of physics. The mathematics and physics are very difficult uh, area, but in order to understand some data systems, we don't need to know about some basic knowledge on complex knowledge on mathematics. You need to understand some simple knowledge on mathematics, but we don't need to learn about some complex knowledge on mathematics or physics because it's very simple. Okay? That's why we use the data design or data systems. Okay, so we can build the where is so in order to build the data system, actually we need to build electric circuit. So, so I believe so I believe you are not familiar. So I believe you don't like this kind of subject, but this is this is some introductory class. So this is kind of some common sense in the uh, engineering. Okay, so actually, so in order to build electric systems, it means we need to build electric circuits. Okay, electric circuits. So what is and then as I mentioned, the electric circuits includes the signals like voltage, current, 전류, 전압, 전류, the voltages, current, or some components like the resistance, inductance, and capacitance. Okay. So actually, the real world. So yeah, just working on working around between the real world, what is the world, but in the real world, in order to build the system, then we need to build the electric circuits. Then, as I mentioned, the electric circuits includes the signals such as the voltages, currents, and resistance, inductance, and capacitance. Okay. So, in order to build the electric system, we need to build these systems using integrated circuit. It's called the IC, integrated circuit. So this is the very small electric circuits composed of several transistors. Okay. So this figure shows the first integrated circuit by Jack Kirby. So I mentioned that using the semiconductor technology, we can build transistors, and then using transistors, we can build basic digital gate. Okay, so historically, the means actually the digital circuits or electric circuits start from the integrated circuit that is composed integrated circuit, which is composed of several transistors. Okay, so this is the very first transistor invented by Jack Kirby. So you can find that so some nodes, so electric wires are connected to some device. So this is a kind of a transistor. Okay, the first transistor, and then this is so you can find that this is the first monolithic silicon IC. So, the semiconductor. The semiconductor is manufactured using silicon, right? Si, silicon. So this is the first silicon integrated circuit. The silicon transistor manufactured. So the silicon IC by Robert Noyce. He was working for Fairchild Semiconductor. The Fairchild is very historically very popular a semiconductor company. So it became Intel. Okay, Intel. The most popular CPU was semiconductor company in this world. Okay. The NVIDIA is a kind of more popular, but actually the Intel is the very popular and the innovative semiconductor technology company. Okay, it's a failure. So using actually using silicon, then we can build a transistor. Okay. Yeah, actually this is very simple. Actually, this photo shows the one transistor. Okay. Then the circuit became more complex. So this is the early design, and actually in the previously we drew some circuits on the paper, and then using some design the drawings, then we can build some semiconductor. It's a PSI, so it's a kind of chip. Okay, and then it becomes like this. So early this IC design. So you can find that some components are connected, and then so you can find some photo of some transistors in here. You can find them Intel here. Okay. So, but currently, and then this is so kind of the first processor manufactured by Intel. So launched in 1974, and then the frequency 2 megahertz, not gigahertz. And then it's a technology node. So I believe you are familiar with some technology node like the 3 nanometer or 5 nanometer in semiconductor technology. But you can find that this is 6 micrometer, like the 6,000 nanometer. So currently we are measuring 3 nanometer technology. The number of transistors is 4.5K. But modern CPU chip, the technology now is a kind of old, right? So recently we are using 5 nanometer or 3 nanometer technology. But so in this example, so I just showed the Intel CPU manufactured using 22 nanometer technology. And then number of transistors, 5.69 billion compared to the 4.5K. Oh, it's very complex. So many transistors. So which means that CPUs are very complex systems. Okay. Then but the start point is very simple, like digital component. So we will learn how we can build these complex systems using basic from the basic. Okay. Okay. So I will stop here. Then, okay. Any questions? Okay. Thank you for listening, and then see you in the next class. 감사합니다.